I want to go through an introduction with you on electron configurations. In your textbook, this is covered in section 8.3. Now, as we get into the details of electron configuration, what this is going to do is this is going to show the specific orbitals that are occupied with electrons for an atom. We're always going to talk about ground state electron configurations, which means that it's going to be the lowest energy orbitals that will be filled for the atom, and it's going to give rise to the lowest energy placement of the electrons for the atom. Typically, our orbitals are going to be filled from lowest energy to highest energy. And as we go through all of these discussions, you should be aware of the quantum numbers that can be used to describe each of the orbitals that we are going to discuss. So as we went through our discussions for quantum numbers, we know that it's that n quantum number that really is the one that we have a choice in. All of the rest of the quantum numbers follow based on our choice of n. So if n is equal to 1 in the first shell, we know that that means that the only value of L we can have is also 0, and the only value we can have for m sub L is also 0. So that combination of quantum numbers of 1, 0, and 0 gives rise to one orbital. The n equals 1 tells us it's an orbital in the first shell. L equals 0 tells us it's a spherical shaped orbital, so an s orbital. M sub L tells us that there's just one of those spherical shaped orbitals. So in the entire first shell for any atom, there is a single orbital that we call the 1s orbital, and it holds 2 electrons. In the second shell, we have a 2s and a 2p orbital. For the 2s orbital, that's going to mean that n is 2, L is 0, M sub L is 0. And for the 2p orbital, n is 2, L is 1, and n sub L can be -1, 0, or +1. So that as I look at all these possible quantum numbers for the second shell, my first set of quantum numbers describes a single 2s orbital that will hold 2 electrons. N tells us it's in the second shell, L equals 0 tells us it is an s orbital, and m sub L tells us that there's just one of those s orbitals. As we look at the quantum numbers for the 2p orbital, N tells us that this orbital is in the second shell, L tells us it's a dumbbell-shaped orbital, and m sub L, having 3 values, tells us that there's going to be 3 dumbbell-shaped orbitals. And as we start talking about all of our orbitals, these 3 2p orbitals that we're going to have are going to be the px, the py, and the pz orbitals. They have a different orientation in 3-dimensional space. Each of them can hold 2 electrons, so that in total I can place 6 electrons across those 3 p orbitals. Now, when I have orbitals like these 3 2p orbitals, orbitals that are the same size, the same shape, and the same energy, these orbitals are said to be degenerate. And this is an important term because, as I said, this applies to orbitals that are equal in size and shape and energy. When I look at my orbitals in the third shell, I have the 3s, the 3p, the 3d. My 3s orbital is going to be spherical and shaped. For my 3p set of orbitals, I will have m sub L values of -1, 0, and 1. I will have m sub L values that tell me there's going to be 3 degenerate 3p orbitals within that shell. And when it comes to my d orbitals, n is going to be equal to 3, L is going to be equal to 2, and in the third shell, that is my maximum value of L because n minus 1, 3 minus 1 is 2. And my m sub L values range from -2 to +2. So I have a total of 5 m sub L values, which means I will have 5 degenerate d orbitals, where the shape of those d orbitals will be that they mostly have 4 lobes. When I place electrons into orbitals for my atoms, I'm going to be placing electrons into orbitals from the lowest energy orbitals to the highest energy orbitals. As I place electrons into orbitals for each atom, I'm going to be starting for each atom with those lowest energy orbitals. So if I look at the orbitals in the first 3 shells, my 1s orbital is lowest in energy and will accept the electrons first. Then the 2s, then the 2p, then the 3s, and the 3p, and the 3d. Now, there's 3 rules for electron configuration that I want to make sure you know about. And the first one is the off-bow principle. And the off-bow principle says that electrons will always occupy orbitals in a way that minimizes the energy of the atom. Now, a couple key words I want to make sure that you pay attention to, and that is that our electrons will always occupy the orbitals in a way that minimizes the energy of the atom. Most of the time, that means that our electrons will be placed into lower energy orbitals before placing the electrons into higher energy orbitals. But anytime we have an exception to our electron configuration rules, that exception will always be in place because the result of that exception is something that does minimize the energy of the atom. And we'll get into those details a little bit later on. My second rule for electron configurations is the Pauli exclusion principle. And this tells me that every electron in my atom must have a unique set of quantum numbers. So right now, I know that each orbital in my atom has a unique set of quantum numbers. I know that each orbital can occupy 2 electrons. But in order to allow 2 electrons to sit in an orbital, each of those electrons must be assigned a unique set of quantum numbers. And so that's where the 4th quantum number comes into play. The 4th quantum number is this magnetic spin quantum number, and all electrons have a value for the m sub s quantum number. There's only ever 2 possible values that we can assign: spin up with +1/2 or spin down at -1/2. I can show an electron that is spin up as either a double-headed arrow or a single-headed arrow that points up. I can show an electron that is spin down as a double-headed arrow or a single-headed arrow that points down. Those are the only 2 values. It doesn't really matter which one you assign to a particular electron as long as each electron in the orbital has one of the m sub s quantum numbers. The significance of the m sub s quantum number is that it is the reason that 2 electrons can occupy an orbital. Without that m sub s quantum number, our electrons do not have different quantum numbers. So that if I look at the 1s orbital, I know that the n value for the electrons in the 1s orbital is 1 because it's in the first shell. The value of L that I have is 0, and the value of m sub L that I have is 0. So this describes a spherical shaped orbital in the first shell where I can hold 2 electrons. Electron number 1, as it sits in that 1s orbital, has an n quantum number of 1, L equals 0, m sub L equals 0, and an m sub s value of, say, +1/2. Electron number 2 then has a value of n that is equal to 1, L that is equal to 0, m sub L that is equal to 0, and m sub s that is equal to -1/2. So that m sub s is our magnetic spin quantum number. There are only 2 values. An electron in an orbital can have either value of m sub s, such that when 2 electrons occupy an orbital, each electron will have a different value of m sub s. When it comes to Hund's rule applies to cases where we are filling degenerate orbitals. Degenerate orbitals occur when we have more than one orbital in a subshell. So for example, this will apply to our p, d, and f subshells. Hund's rule says that when we fill degenerate orbitals with electrons, we will place one electron in each orbital before pairing the electrons. So that what this looks like is that if I place electron number 1 into my p subshell, it will go there. So we'll call this electron number 1. Electron number 2 then is going to go into a separate 2p orbital such that the spins are parallel. Electron number 3 goes in that third degenerate p orbital. Now that I need to place electron number 4 into the orbitals, only now do I begin to pair those electrons up. So electron number 4 gets placed in this orbital with a spin opposite that of electron number 1. Electron number 5 gets placed here with a spin opposite that of electron number 2. And electron number 6 is placed there with a spin opposite that of electron number 3. So that as I place the electrons across those 3 degenerate p orbitals, I placed one electron in each of the 3 orbitals such that those 3 electrons had a parallel spin, meaning they were all spin up or all spin down. And then once I got to electron number 4, that was when I began to pair the electrons up. Why do we follow Hund's rule? Why is this important? This is important because of energy. Almost everything we talk about in the context of electron configuration, almost every why, has to do with the energy of the atom. It is lower in energy to spread those electrons out for electrons 1, 2, and 3 than to immediately begin to pair them up. We're giving each electron its own region in three-dimensional space that it can occupy. Electrons have negative charges, so to place 2 electrons into a single orbital, there is a little bit of repulsion that we will see between those electrons, so it's better to space them out initially.